Okay. Hi, everyone. So at New York University, I work at the Music and Audio Research Lab, MARL, where I lead work in music information retrieval and digital signal processing. So it is from this perspective that I want to talk to you about the use of computational approaches for the modeling, or rather more precisely for the measuring of rhythm similarity in music. Now, there was a very interesting discussion about this yesterday, and one of the questions that came out of that discussion was about the motivations for doing this type of work. I mean, why would we want to do this? And there are many things I could think about. For instance, in computational musicology, these type of approaches could help the study or the understanding of the relationships that exist between music from different styles, from different cultures across the world, very much the way that Godfrey has been pioneering that, or to take another example from Xavier's talk, he also talked about many ways in which you can do this. In music information retrieval per se, of course, this could be part of engines for music recommendation or music discovery, maybe for automatic playlisting, for auto-tagging or general music classification, and many other things that I'm really not mentioning now. So perhaps a good starting point is to really define what we mean by computing rhythm similarity. It's a very personal view, but in my view, I think what this means is to use algorithmic methods for taking music data and projecting that data into a feature space. And in that feature space, rhythmically similar music is close together, according to some predefined distance function, say a Euclidean or a cosine distance. I'm going to further narrow this to say that when I say music data, what I really mean are music audio signals, so that the music in those signals can be polyphonic, can be multi-instrumental, can be both, that the process of computing similarity is fully automated, and that I have no access to any prior information about the music, meaning that the process is blind. Of course, after features have been extracted and distances have been computed, I still have to know if this thing is doing the right thing. So validation is an issue, because similarity ground truth is not readily available. And researchers, and I'm no exception, turn to genre classification as a proxy task for music similarity. And of course, this comes with a very strong assumption that in certain music styles, like dance music, or maybe music from Latin America, or maybe music from Africa, there is a very strong, even unambiguous dependency between genre classes and rhythmic content. And this is a very arguable assumption at best. In any case, what I think is important from the definition I gave above is to realize that the process of extracting features from the audio signal is the most important part of this process. And in designing this feature extraction process, we want to make sure that the representations that we obtain have certain qualities. And there are a number of qualities which are discussed in the literature, but I want to focus on 4. First, that these representations are able to encode the relative positions of events in a manner that is sensitive to the relative order of those positions. Second, that these representations are invariant to tempo, at least to some extent. Third, that these representations are able to characterize information that occurs at different frequency ranges separately. And we can say that this is a very, very, very coarse approximation to the process of timbre differentiation that Stephen was talking about earlier today. And 4, that these representations are robust to variations introduced by non-rhythmic content. So how do we go about doing this? Well, this is, as the title says, a very limited literature review. I try to include some of the most often cited works in the literature. And instead of actually giving you the detail of what everyone does, I just wanted to give you a quick idea of what are the most common techniques used to achieve these goals. So for instance, in order to encode relative positions, people use standard periodicity analysis tools like the autocorrelation function, ACF, the discrete Fourier transform, DFT. There are exceptions, I don't know, like the rhythmic patterns that were suggested by Simon Dixon and Fabien Goujon back in 2004, but by and large, ACF and DFT dominate the field. Yeah. Second, that in order to de-emphasize non-rhythm information, people use across the board the same 2 strategies. One is to base all the analysis in novelty functions, or also known as onset detection or onset strength signals, which already get rid of a lot of non-rhythmic information. And second, that the process is performed locally on a frame-by-frame basis, and then at the end is aggregated across the entire time length of a signal. And the reason for doing that is that you assume that rhythmic content is heavily repetitive and is therefore going to survive that aggregation, and everything which is not repetitive is going to be smoothed out of the process. Yeah? Interestingly, very few approaches in the literature actually make use of any notion of timbre or distribution of events in different frequency bands. There are two of the approaches in the list that actually do so, and they show significant improvement in terms of their results. Yeah? So this is an important component to add to the analysis. And where most of the difference in the literature lies is basically in how do you make your representation tempo invariant. And there are many different approaches and many different ways in which I could classify those approaches, but I'm going to give you a very simple one. I'm going to distinguish between those approaches that achieve full tempo invariance, meaning that if I have a rhythmic pattern at 60 BPM and I have another rhythmic pattern, or the same rhythmic pattern at 320 BPM, the final representation is going to be the same. Yeah? I have full tempo invariance. Or approaches that have only partial tempo invariance, meaning that the output representation is only going to be the same when the tempo variations are within a certain range, say plus minus 5% from the BPM value. And interestingly, at least for the data sets that we use for validation, and that's a big at least, the partial invariant approaches perform as good or sometimes better than the full invariant approaches. And we could discuss that further later on. Now, I wanted to give you a little bit of detail on what are the choices that we make throughout this process. But because we have no time to talk about all the approaches that I presented before, I just want to pick one of those, one case study, and it's a representation which is known as onset patterns. There are several papers that contribute to their origin, but I would cite the paper by Paul and his colleagues in Austria back in 2009, where the term onset pattern was actually coined. But a lot of what I'm going to talk about actually derives from other people's work, including Andre's work in this area. So the way this goes is first you have your audio signal, so you calculate some time frequency representation. In this case, a log frequency short time Fourier transform. Then for each one of the bands of your analysis, you calculate a novelty function. And the way you typically do this is by measuring some notion of flux between the elements on that frequency band, with some smoothing here and there. You know, there are some very specifics to how this is calculated, but it gives you something like the plot on the far side of a slide. Then you apply a nonlinearity to these novelty functions, typically compression, and then you subsample the entire representation to fewer frequency bands. And this process of subsampling is going to come up several times throughout. Then for each one of those bands, you have a moving analysis window. Now, the length of that window is a very important parameter, because if you want the window to be long enough such that you capture some information at the metrical level, but you also need the window to be short enough such that the assumption of a stationarity, which is crucial when you do periodicity analysis, is still viable. And that's a difficult trade-off to reach. So after you have your window, on that window, you compute basically a magnitude spectrum. Yeah? And this is important for several reasons. First, because the spectrum is an analysis of periodicities in the signal, meaning that what you're encoding are relative positions of events, not the actual exact positions of events, and that's what we want for this. Second, because you're doing the magnitude spectrum, meaning that you're throwing phase. And by throwing phase, you're making the analysis shift invariant in time, meaning that if I have a certain pattern within a window, and then I have the same pattern shifted a little bit in time, still the magnitude spectrum that I obtain from this representation should be the same. But because phase does play a role in the computation of the Fourier transform, the patterns of phase cancellation that occur between different events that might be synchronized or not in the signal introduce some sensitivity to the order of relative positions in the signal, meaning that if I have a pattern 2, 1, 2, 2, or I have a pattern 2, 2, 2, 1, even though they have the same distribution of inter-onset intervals, the magnitude EFT is actually going to be different for both those patterns. And this is very important to have, and it extends, that sensitivity extends to more important things like meter and groove, you know, which of course you want your representation to be sensitive to. The final thing I want to say about the computation of the magnitude spectrum is that you want your frequency axis to be logarithmic, not linear. Why? Well, because in the log frequency axis, changes of tempo are manifested by shifts in frequency of the pattern of peaks that you have in the spectral domain. While in the linear axis, those same tempo changes actually manifest by a change in the distance, in the relative distance that exists between those peaks. So of course, the representation that I obtain when I use linear frequency is going to be different when I have changes of tempo, and the one that I obtain when I have a log frequency is only going to be shifted. And when you combine this, and this is a very clever thing, when you combine this with very low resolution in your Fourier analysis, it means that certain shifts in frequency, they actually come up as the same in the representation because you don't have enough resolution to actually see the variations between those. Yeah? So then you have a little bit of tempo invariance in your analysis. And that's when I say partial tempo invariance, this is what I meant. Okay. So you do this across all the frequency bands. So in this representation, in the y-axis, you have the frequency bands. In the x-axis, you have the periodicities coming out of the Fourier analysis. So you have this 2D map, which is what we call an onset pattern. You post-process it a little bit, so you subsample the whole thing into fewer subbands, just to make the representation a little bit more compact. And you weight, you apply some multiplication with a normalization matrix in order to compensate for distortions that come up in the process, and also to emphasize certain events in the 2D map over others. And this is a tricky thing, and I'm going to talk a little bit more about this later. And then at the end, as I mentioned at the beginning, you just simply take all these frame-based onset patterns and you aggregate through time, using the mean. So you have a mean onset pattern, and that's what you use to represent the entire signal. Okay. Now, there are a ton of parameters in this process, and choosing the right parameters to get the best result is a complicated thing. It's where the art of this thing is. Andre did some very interesting work back in 2011, where he did a systematic analysis of the impact of these parameter choices in this system. And he came up with some very good suggestions for how you should choose your window length, how you should choose the resolution of your periodicity analysis, what should be the order of sampling operations, or whether that order matters or not, and many other things which are not mentioning here. But I'm going to say that this type of analysis is based on an exhaustive search of the parameter and value space. And this is, of course, not possible when you have very high dimensional parameters spaces, or when you can really, or you really want to see the impact of certain parameter or all possible parameter combinations and value combinations that you might have in this space. And I'm going to go even further to say that even in this context, when we talk about parameters, we're talking about relatively high-level parameters, but we have no control of low-level parameters. Like, for instance, when you do a DFT, you're using a filter bank, and you have very specific filters that you use, and those filters, you have no control on the design of those filters. So maybe there is a design or a different iteration of those filters that will be optimal for this problem, but we don't know what it is, and we have no way to explore it, or at least no easy way to explore it. So I'm going to suggest an alternative view, and I'm going to say, well, what if we think of rhythm similarity systems as a combination of basically two types of operations? One type of operations are subsampling operations, like the ones I mentioned before. So you have an input representation, you have a small neighborhood, you compute the mean, and then you downsample, which is something that signal processing people do all the time, and in machine learning people call pooling. And then the other type of operations are affine transforms of the form defined by the equation there. And in that equation, X is the input, Y is the output, W is a matrix of weights, D is a vector of biases, and H is a nonlinear function. So let's say that I choose W to be this. I choose the bias to be 0. And I choose a nonlinearity to be the log 10 of the absolute value of whatever I put inside. I then obtain the log magnitude DFT. And I could choose values for W, B, and H such that I have, for instance, the scale transform that Andre proposes in his papers, and that he'll probably talk about tomorrow. Or you could choose those values to have PCA, or you could choose those values to have novelty detection. All of these operations are simply single instances of a larger family of functions which are defined by the equation there. And what is even more interesting is that this family of functions can be implemented as a neural network such that the weights and the biases can be learned through standard optimization processes. And there is a huge literature, of course, dating for many years about this very specific type of formulation. So let's prove the concept. And let's say that I take onset patterns, but I take the onset patterns at a much higher resolution, both in frequency and in periodicity, than the optimal resolution suggested by Andre on his paper. Yeah? And then I say, well, I don't know how best to subsample this, and I don't know how best to normalize this. Thank you. So basically, I combine all subsampling and normalization into a 3-stage neural network with those parameters there, and we can talk about the details offline. But the thing to mention here is that thing has more than 900,000 parameters. So it's a really large parameter space. And then I use, as I say, standard optimization techniques, stochastic gradient descent and backpropagation to train this thing and try to obtain the best subsampling and the best normalization operations that I can get for this particular task. And when we run this on the Latin music dataset, which is one of the standard datasets used for the validation of rhythm similarity approaches, using tenfold cross-validation on genre classification and aggregating the outputs just by summing per frame, we obtain an accuracy of 83%, which is not where we want to be, but as far as I know, is at a state-of-the-art level. Yeah? And this is a very preliminary version of the thing I'm talking about. This is just a small part of the entire system, but what we're really after here is this notion of making this into a fully fledged deep learning architecture, yeah, where the multiple stages are all these stages that I've been talking about in the past few minutes. So you have novelty analysis in one stage, you have periodicity analysis in another stage, you have maybe the scale transform as another stage, maybe you have dimensionality reduction and classification. So the entire path from signal to classification or similarity is learned. Yeah? The optimal representation or the optimal set of filters and biases and nonlinearities for this to give you the best possible results are learned. And we can do this as long as we have access to a lot of data. So that's a caveat, yeah? Data. These things are data hungry, yeah? And those are the bad news. The good news is there's been a lot of research in machine learning for the last few years that allow for this to be mostly optimized using unsupervised learning. And what that means is that, yes, we need a lot of data, but most of the data that we need doesn't have to be annotated. It's just audio that we need to give the machine, yeah? And only a small amount of the data has to be annotated to do what they call supervised fine-tuning, to basically take a general representation and fine-tune that to a specific task, in this case, rhythm similarity. Okay? So just to summarize, the walkout message is rhythm similarity approaches can be conceptualized as deep architectures. If you take it one step further, they can be conceptualized as deep learning architectures, so all the parameters in this entire process can be learned. And I want to really emphasize this is not unique to rhythm similarity. This can be applied to any of the tasks which are currently, well, to many of the tasks, content-based tasks that the MIR community, for instance, is looking into. And in this particular context of rhythm similarity, preliminary tests show that we can achieve a state-of-the-art performance even with a very limited implementation of these ideas. So what is next? Well, the obvious next step for us is to take this thing and start to go closer and closer to the signal level, yeah? To implement many more multiple stages and substitute these hard-coded stages that we currently have in our system, yeah? And this is something that, at least for Western music and for Western pop music, we can do right now. We have enough data to do this. We've been actually doing this for chord classification. We've been doing this for instrument recognition. And we already have state-of-the-art results in all those areas. But we haven't been doing this a lot from rhythm because for these particular collections, it doesn't seem that rhythm is the main factor for similarity. And I think that's where a conversation about other types of collections of music is very relevant. And then, of course, there are many issues with architectural design and the choice of hyperparameters that require domain knowledge. And when I say domain knowledge, I'm talking about neurological knowledge, I'm talking about cognitive knowledge, I'm talking about musicological knowledge that really should inform this process at the meta level. And those are many conversations that we need to have with people like you. And then, of course, this entire process can be used as a way to learn about the task that you're trying to perform, because this is a data-driven way to get a system that gives you, say, good results for rhythm similarity, meaning that you can go back and see what the system learned and maybe understand what are the important, like statistically important patterns that allow you to say these two things are similar or not. And that could possibly give us a different pathway to understanding what it really means for two things to be similar, what it really means for two things to be part of the same genre, what does it mean for these two things to be C major, I don't know. Finally, we need more data. and we need much better evaluation strategies. And this is something that connects a little bit with the talk by Fabian and André earlier today, but to a lot of the conversations that we've been having here. MIR is a goal-oriented field, and a lot of what we do is just to maximize a certain classification accuracy, but we are really not aware, or sometimes we don't pay enough attention to a lot of the processes that allow us to go from A to B. And that's where I think the conversation with other fields could really help. And with that thought, I'll finish my talk with thanks to a lot of people in my lab that help in this research. So thank you very much.